Welcome to chapter 15. This chapter is all about regression, linear regression, simple and multiple regression, constructing regression models, interpreting and visualizing regression results, and so on. So let us begin with exercise 1. The goal of this exercise is to confirm that we can implement the math that I showed in this chapter to reproduce the results that statsmodels.ols, OLS, of course, stands for ordinary least squares, will output. Okay, so using the ice cream happiness study that I showed earlier in this chapter, these are fake data, just a funny example to give us some numbers to work with. What you want to do in this exercise is construct a design matrix and then compute the vector of coefficients, the beta coefficients, by directly implementing the math. And then you can confirm your results against the output of stats models sm.ols. And I've actually already done this for you. I've already shown you the regression coefficients earlier in this chapter. Okay, so let me scroll up to equation 10, and then I will switch to Python and show you the implementation. So here is the formula that we use to compute least squares and obtain the unknown beta coefficients given the observed data in vector y and the design matrix x. And the design matrix has columns corresponding to independent variables and rows corresponding to observations. So we have the inverse of x transpose x times x transpose times y. And all you need to do in this exercise is build matrix X and implement this formula directly, and then confirm that your beta coefficients match the output of statsmodels.ols. Okay, so now I'll switch to Python and show you the implementation. Here I have the data again. So how many ice cream cones someone ate in the past month and how happy they were in the past month. Okay, here I'm creating the design matrix, and actually maybe before running the rest of this code, I will just show you this design matrix. So here we have the intercept here, and here is the ice cream cones, the number of ice cream cones eaten in the past month. Now, sometimes in models, people put the intercept as the first column, sometimes as the last column. The order of the columns actually does not matter as long as you know which ones to interpret. So you don't want to mislabel this as the intercept. Of course, that would be wrong. But as long as the column labels are correct, it doesn't matter what the order is. That has no impact on the model fitting or any of the results. Okay, so let's see, with that visualized, now here's where I compute the main line. So this is called the left inverse. Here I have x transpose times x, and then the inverse of that matrix times x transpose. This is the indicator for matrix multiplication. And then we simply multiply the left inverse by happiness. Now you could put all of this into a single line of code if you want. You just take all this and stick it right here. But yeah, I split it up into 2 lines just to try to make it a little bit easier to visualize. Okay, so then we can print out the betas. And here I have in the comments, this is the output from a statsmodels.ols. I showed this earlier in the book chapter, and you can also reproduce it. We're going to reproduce this later as well. So you can confirm that this number matches this number matches this number. Basically, that just shows that the math that we have implemented here is consistent with what you get as the output from statsmodels.ols. Now, that said, I generally do not recommend implementing this equation on your own in general. That's because there are numerical instabilities. There can be inaccuracies when trying to explicitly invert this matrix for some kinds of models, especially if you have a lot of a big data set and a lot of regressors, or if the numbers span very different ranges. If you have different numerical ranges for different independent variables, this line can actually be numerically problematic. So in practice, you want to implement more numerically stable algorithms for computing the least squares problem. That is a level of mathematical linear algebra detail that I do not discuss In this book, I do discuss it in my other linear algebra books, but don't worry, you don't have to worry about that math. As long as you understand conceptually what this line of code does, and also this line, then that's totally fine. You let sm.ols take care of the low-level implementational details. This is the video for exercise 2 of chapter 15. There are two concepts of regression that we will explore in this exercise. One is the difference between regular vanilla R squared and our adjusted R squared for evaluating the model fit to the data. And the second concept that we will explore here is overfitting data with noise. Okay, so here's what you want to do. It's going to sound a little silly, and then it's going to get even sillier and weirder. But I hope you enjoyed this demonstration. So generate a data set where the dependent variable is 100 numbers drawn from a normal distribution. So literally pure random noise, just random numbers drawn from a normal distribution. And the independent variable is also another 100 random numbers. No correlation. You don't need to impose any kind of relationship between these two variables. Literally 100 random numbers and 100 random numbers. Okay, then create a design matrix with two terms. There's going to be an intercept term and this random numbers term, this independent variable. Run the regression model, use statsmodels.ols, extract the R squared and adjusted R squared terms, and then just report them. And yeah, as I say here, this is kind of a ridiculous thing to do. We are trying to predict random numbers from other random numbers. So of course, we expect the R squareds to be around 0, and that's what we find in this particular case. Okay, so that's part 1. And then part 2 is going to be to make a small adjustment. So instead of having only one independent variable, or I guess 2 if you include the intercept, come up with a design matrix that has 37 independent variables, all random numbers. So instead of trying to predict one set of random numbers from another one set of random numbers, try to predict one set of random numbers from 37 sets of random numbers. So in this case, you're going to have a design matrix that has 38 columns, 37 columns of pure random numbers, no relationships between them. You don't have to impose any correlations or anything like that. Purely random numbers, and then an intercept term. And then again, report the R squared and adjusted R squared. And you will find, strangely enough, that the R squared is pretty high. R squared of 0.3 seems like a pretty respectably high number for an amount of variance to explain. And yet these are all random numbers. This also doesn't make sense. It's negative, which is mathematically possible for adjusted R squared, but it indicates that something is horribly, horribly wrong with the model. Okay, so there's more to do in this exercise. You're going to run an experiment, but I want to first switch to Python, show you the code for the solution for this exercise so far, and have a short discussion. And then we'll come back and I will explain the experiment that you are going to run. So here we have a sample size of 100. The dependent variable is random numbers. And here I have the independent variable. This is also random numbers. Okay, then I fit the model, adding a constant term to the model, and then reporting the R squared and the adjusted R squared. Okay, so then, you see, again, they're close to 0. Not surprising, right? Trying to predict randomness from randomness. It should be 0. Okay, now the second part, we just need to change this from 1 to 37. And now, again, we get an R squared that is pretty, it's a modest effect size. It's a decent effect size, which is really weird considering there is no effect to find. And the adjusted R squared is also pretty moderately sized, but negative. Again, mathematically possible, but totally uninterpretable. If you ever see a negative adjusted R squared, something is horribly wrong. Something is very wrong with the code or with the model or with the data. And then there's just this little bit of code here. This is just to show that the R squared, not the adjusted R squared, I show the formula for that in the book, but just the regular vanilla R squared. It is literally just the correlation between the predicted data and the observed data. So this is just a quick demo of that. So here I have the dependent variable. This is the independent variable, the predicted data here. So I'm saying model.predict, and then input the design matrix, and then correlate that and square the correlation coefficient. And yeah, you can see it's exactly the same number as the model dot r squared. Okay, so now I'll switch back to the book and explain the rest of this exercise. Now, what you want to do is run an experiment in which you systematically vary the number of independent variables. So previously, we just did one independent variable and 37 independent variables. Now you want to systematically vary it between 1 and 100. And you want to repeat this multiple times. So for each number of independent variables, repeat the experiment 50 times. So 50 times you generate a new random DV and a new set of random IVs. Fit the model again using statsmodels.ols. Again, extract the R squared and adjusted R squared, and then make a plot that looks like this. So what do we see here? On the y-axis is the R squared terms, so variance explained. And I've just scaled it up so it's in percent instead of proportion. And then you see for the R squared in the dark gray boxes and adjusted R squared in the light gray circles. And then here I have 0 uh, indicated with this dashed line. And then here I have the number of independent variables. I have converted this into a fraction of the total data points. So instead of going from 1 to 100, it goes from 0 to 1, where each number would be a fraction of the total data points. And the reason why I do this conversion here is in case you want to change the number of data points. So here we are simulating 100 observations, but maybe you want to try it with 1,000 observations or 23 observations. So this just helps you interpret this, basically the fraction of total data points that we have. You can also convert this into the, loss of degrees of freedom or something like that. Okay, and then the final thing I'll mention before switching to Python is that each one of these markers here is actually the average of 50 different R squared terms or adjusted R squared terms. So that's because for each of these number of independent variables, you want to repeat the experiment with new random data 50 times and then average them together. That just increases the stability a little bit. So here you can see I've also soft coded the number of IVs. Instead of going from 1 to 100, I've soft coded it to go from 1 to n, where n is the sample size, the number of data points we have. And then, yeah, I'm skipping by 3 just because, we don't need to do every single step, so we can skip by some number. Okay, so here we have one for loop that runs over the number of independent variables and another for loop that goes over the experiment repetitions within each number of variables. Okay, so then you can see, this code is basically the same as it was before that I already showed you. So here we have the dependent variable, the design matrix. Here I add the intercept or the constant term, fit the model, and from here I can extract the R squared, adjusted R squared, multiply it by 100. In this case, the way that I am going to average over all 50 of these iterations is by summing the results. So I'm just summing, and then here I divide to give me the average. And dividing by the number of experiments plus 1, and that's because this looping index goes 0 through 49, and we have 50 iterations in total. So if I would divide by xi here, then it would actually not be the average. It would be dividing by n minus 1, but we need to divide by n. Anyway, that's just the way that I implemented it. Okay, the rest of this code is pretty straightforward. We are just plotting, scaling by n, and then plotting the results. So here is the graph. And again, you see that the R squared is just increasing with the number of independent variables, whereas the adjusted R squared is basically hovering around 0. And we get some negative signs here. You can see if you run only one experiment iteration instead of 50, then this will start getting wild. This really gets all over the place, but it becomes large positive, large negative, so they average out to zero. As I mentioned, when the adjusted R squared is negative, something is horribly wrong. Now, something is horribly wrong here. We have a really complicated model, lots and lots and lots of predictors, dozens of predictors, all pure noise trying to predict another variable that is pure noise. How does this work? Why this is crazy that the R squared is so high, the correlation coefficient is so high? The answer here, what is happening here, is just pure, simple overfitting. We are massively, massively overfitting the data. And to demonstrate how incredible this overfitting is, we can compute the R squared for these data and for new data that are drawn from the same population. So this is more random data, but the mean and the standard deviation is the same as what generated these data. So new data drawn from the same population. If this were a good model, the model should predict data from the same population that we have not yet measured. That would be a demonstration of generalization. That shows a good model fit. But instead, what we're going to find is that the R squared is close to 1, 0.99 for these data, for overfitting these data. But for generalizing to new data, we get a correlation squared of 0.02. We can be generous and round up to 0.02. But this is absolutely insignificant. This is basically just 0 plus a little bit of rounding error due to noise. Welcome to exercise 3 of chapter 15. This exercise is a little bit more open-ended than most of the exercises here because I want you to have the freedom to customize and implement this exercise as you see fit. So basically what you want to do is go back to the data for simulation example 3. Now, all the data to produce, or the code to produce those simulated data are in my online code file, and I'll show you the code in a moment. So you certainly need the code for this chapter to create those data. But once you have those data, I want you to have the freedom and flexibility to do whatever analyses and visualizations you think are appropriate based on your intuition, your experience, and of course, based on what you learned in this chapter. So here is the code that generates the data for example 3. So here I'm generating the data. Remember, this was the data about predicting exam scores based on how much people slept on average and how much people studied for the exam. So here is some visualizations that you see here. So we have the dependent variable exam score on the y-axis, and on the x-axis we have how much people slept on average before the exam, and then it's stratified or grouped according to how much people studied, how many hours people studied. So what you see is an interaction between how much people sleep and how much people study on their exam scores. So here is the data stratified, so grouped into 3 different bins. And here I visualize the data again, exactly the same data, but using color to illustrate the third dimension of data instead of grouping into bins like this. Okay, so there's no analyses that were performed here. That is your job here in exercise 3. So now I'm going to scroll down and show you how I analyzed and visualized these data. Needless to say, you need to run that code for example 3 before running this code. And that's because this variable df data frame gets overwritten multiple times. So you want to make sure that you run that code to generate that data frame immediately before running this code. Okay, so here I extract 2 columns from this data frame, the DESMAT, which stands for Design Matrix, and the dependent variable. So here I'm just dropping exam score, and here I am just extracting the exam scores. And then I put that into sm.ols. So if you want, you could also just have this code immediately in here. But I think it's nice to have these as separate variables because I'm also going to use them in the next cell for the visualization. Okay, so we can run this model. And we can see some overall model characteristics like the R squared is super duper high. Not surprising. These are simulated data, and I didn't create any noise in the data. Here we see the study hours and sleep hours are significant. Actually, all of these terms are significant. Again, not surprising because I simulated the data without any noise. Now, this intercept term is also highly statistically significant. The coefficient is 85. And what does this mean? So this means that the expected exam performance when all the other independent variables are set to 0 is 85% accuracy on the exam. Now, in this case, in this example, in these data, this is not really an interpretable number. And that's because, getting this score would mean that students slept 0 hours and they studied for 0 hours, and yet they still got 85 on the exam. So this is another illustration, which I've discussed multiple times in this chapter, where the intercept term is necessary for model fitting, but it's not necessarily interpretable. Okay, so there's some other interesting things to note about these model diagnostics. I'm going to get back to that in a moment. Okay, so now for the visualizations. So actually, let me just show you the plots first. So what I chose to visualize is the observed data by the predicted data. So here we have the observed exam scores on the x-axis and the predicted exam scores, which is the linear combination of all the columns in the design matrix, where the weights for each column in the design matrix, each independent variable, come from the beta coefficients. Okay, so really tight relationship here. Again, not so surprising. Now here's the residuals plot. Now, by definition, the residuals and the predicted data have a correlation, a Pearson correlation of 0, which means by definition, there is no linear relationship between these two variables. Nonetheless, when you look at this plot, we see some structure in here, right? So there's clearly this is not just an unorganized cloud of mess, right? There's clearly structure going on in these data. And when you look at the histogram of the residuals, that's also very clearly non-Gaussian. These are non-normally distributed residuals. So this indicates some problems with the data. And if we scroll back up to the raw data, you can see why the residuals are going to be non-normally distributed. There is a strong heterogeneity of variance in these data. So the variability is very small over here, and the variability gets larger and larger with increases in the X variable, which in this case is hours of sleep. Now, what to do about this? In general, if you have a regression where you see problems with the residuals, it doesn't mean that you cannot interpret the regression. It doesn't mean that you cannot do the regression, but it certainly means that you need to exercise caution and inspect the data very carefully. So what do we see with these data? We see, the pattern is so clear. Also, when you look at this grouped or stratified visualization, the pattern is so clear that I think in this case, it's completely fine for practical applications that we have violated assumptions of the ANOVA because the data are already very clear when we visualize them. Now, if the data are not so clear, if the patterns are nonlinear, then you would need to be more concerned and take action based on the diagnostics of the residuals of the regression model. In particular, maybe you would want to apply some kind of nonlinear transformation to the data, or some alternative method of nonlinear regression, or some other machine learning method. Welcome to exercise 4 of chapter 15. In this exercise, I'm going to illustrate a different way of using stats models to run your regression analysis. So the way that we've been doing it so far, which is the way that I find most comfortable, so that's why I spent most time on it in this chapter, is to use sm.olfs and then create a design matrix and input your design matrix in a dependent variable and fit the model and extract whatever you need and so on. It turns out that there is another module in stats models, so the same library, but there's a module called formula.api. So what you want to do is input this module using this line of code here. So you can abbreviate it as SMF for stats models formula. And then what you can do is create a string that is a formula for the design that you want to fit. So we say, this is a general term. This is not corresponding to any particular variables. So y tilde x1 plus x2. So this is just an example of fitting a model where y is the dependent variable, x1 and x2 are two independent variables. And then you call smf.ols, this is lowercase, unlike sm.ols, which is uppercase. You input the formula, you input the data as a data frame, so these correspond to the column labels, and then .fit. Now the output of the output of this function, which here I call variable result, is identical to the output of sm.ols, which you've been working with so far. So this is just a different way of obtaining the same result by defining the model in a different way. And so this is not the solution. This is just a little bit of a guide to help you get the solution. So what do you want to do in this exercise? What you want to do is repeat basically the code from, or the results from the previous exercise 6. This actually corresponds to simulation example 3. So run the code, adapt this code here, make sure you get the same result that you got with sm.ols for simulation 3. So this is all the code for exercise 4. It's really straightforward. We just import this module, define the formula. So we have exam scores equals, this tilde is modeled by study hours plus sleep hours plus their interaction term, which we indicate using an asterisk. Again, all of these texts here, these are column names in the data frame. Now, if you run this code and you get weird results or you get error messages, then you probably just need to go back to the code, scroll up, and run the code for regression simulation number 3 that will generate these data with this data frame. Okay, and then we can print out the results here, and you will see that it is all the outputs and also the numbers are identical to those that you will get with sm.ols. Welcome to exercise 5 of chapter 13. The goal of this exercise is to reproduce the results that you got from the previous couple of exercises using stats models, but here you're going to use scikit-learn. In particular, you're going to use the linear regression function that is contained in the scikit-learn library. So you want to input the same data. So this is the simulation about study hours and sleep hours on exam performance. So you've already worked with these data several times, the past couple of exercises, and I talked about it and visualized the data earlier in the chapter. So yeah, what you want to do is just figure out how to use the linear regression function to reproduce at least some of those results. You want to make sure you get the coefficients, the beta coefficients, the regression coefficients, and they should match the output from sm.ols and also smf.ols. Okay, so now I will switch to Python and show you that solution. So this code is also fairly straightforward. There's not a whole lot you have to do, but if you are new to scikit-learn, it might have taken you a little bit of effort to figure out how to get this to work. So basically, we have to create a new model from this linear regression. So this is a new instance of this class. And then we use the method .fit, and you input two variables, x and y. That's what I call these variables here. X is the design matrix, and y is the dependent variable. And now here I'm printing out the intercept and the beta coefficients using the model after it has been fit, .intercept and .coef for coefficients. And yeah, you can scroll up and confirm that those are the same as what you get here. For example, the intercept is 85 and so on. Now, the thing is, scikit-learn is a really great library for lots of things, but if you are interested in evaluating statistical models, not just getting the coefficients, then scikit-learn is pretty limited, right? So it doesn't compute a lot of these diagnostic tools that you get for free. So we have diagnostic tools about the model, diagnostic tools about the data, and about the residuals. That comes standard in stats models, which is really great, really helps you interpret the model. And from scikit-learn, all you get are the coefficients, basically. So in my opinion, if you're doing statistics and regression, then stick to stats models library. Here we are in exercise 6 of chapter 15. I really enjoyed making this exercise for you, and I hope you also enjoy working through it. The goal of this exercise is to write an algorithm that will find the optimal breakpoint in a piecewise regression. So let me see. So we start with figure 15, and actually I'll scroll it. So this is not figure 15 in this chapter, but it's basically the same thing as chapter 15. So the idea is that we have all of these data. These are the circles, and you can see that it's a piecewise linear relationship between x and y. So it's linear here and is linear here, but it's nonlinear over the entire range of x. So the question is, where do we put the breakpoint? Well, in this simulated data, I created the data, so I know exactly where the breakpoint is. But in real data, you don't know where the breakpoint is. That's something you might want to discover. So the goal of this exercise is to write an algorithm that will discover the optimal, or will try to estimate the optimal breakpoint for this analysis. And you can see in this particular case that the true breakpoint and the estimated breakpoint are kind of close, but not exactly the same. Okay, so how does this algorithm work? So what you should do is, first of all, add a little bit of noise. So basically start by copying the code that generates figure 15. And then you have a for loop where you split the data into two segments using a breakpoint. And in the for loop, you vary that breakpoint from 2 to 8. So one breakpoint per iteration. So on the first iteration in this for loop, the breakpoint is at x equals 2. And then at the next iteration in the for loop, the breakpoint is x equals 2.1, and then 2.2, and so on, all the way up to 8. So you can do actually however fine resolution you want. Okay, so then what you want to do is you have these two sections, two segments, mini data sets. Use sm.ols to fit a simple regression model to each segment, and then compute the Bayes information criteria, the BIC, from each segment, average those two BIC scores together, and then store that for each element in X. Here, this little margin comment is just saying that I have previously in the chapter introduced you to using BIC to compare models with a different number of parameters. In this case, the models have exactly the same number of parameters, but it's still valid to compare, to use the BIC to compare different models that have slightly different parameterizations with the same number of parameters. Okay, so then actually I think I will just explain the rest of this exercise by showing you this figure. So again, here's the data. You can see the x-axis ranges from 0 to 10. And now going from 2 to 8, you're going to loop through in a for loop and have each number be the breakpoint at that iteration in the for loop. So these are the average BICs for the two segments for placing the breakpoint in different locations. And here I have identified the minimum BIC, the minimum average BIC, and this is what we take as our best model. So according to this analysis, the best model had the breakpoint at around, whatever this number is. It's like 2.8, something like that. Actually, I can see it here. It's 2.83 is what happened to be here. Because there's some noise in these data, you're going to find that this bops around a little bit, but it should be somewhere around here. These breakpoints are worse because the BIC is higher. The minimum BIC corresponds to the best model parameter setting. Okay, and then you can generate a plot that looks like this, where you show the data, the true breakpoint here, and the estimated breakpoint according to this model. And well, I'll have a few remarks to say about this. when I show you the code. Here's where I recreate the data. Again, you can do this from scratch, or you can copy the code that corresponds to the previous figure in the book. I set, x-axis values go from 0 to 10. I set the breakpoint, that is BP, breakpoint, to just be 1/3. In principle, you can set this to be any index you want, although I guess it doesn't make a whole lot of sense if you start at the very beginning or the very end, but I just arbitrarily set it to be 1/3 of the way through. Okay, and then here's where I define the two different relationships. So I'm creating these two segments here, y1 and y2. y1 is a function of x, so we're scaling x by 1.2, so it has a steep slope, and y2 has a gentle slope, and then I just paste these together. Now here what I'm doing is just shifting y2 so that the first data point of y2 is the same as the last data point of y1. That gives us this continuous function. Okay, and then I concatenate these two together and add a little bit of noise. Now, once you finish implementing this exercise, I encourage you to play around with this amount of noise and see how robust is your algorithm to find the optimal breakpoint to the amount of noise. Okay, but I'll leave this at 0.1 for now. Here I define the breakpoints that I'm going to empirically evaluate. They will range from 2 through 8 in 37 steps, because why not 37? It's a great number. Okay, here I loop through the data, or I loop through all the different breakpoints. This is where I split the data into the two different segments. So the data before the breakpoint and the data after the breakpoint. And then I run separate regression models for each of these segments, extract the Bayes information criteria, and average them together. And then we can just find the minimum. So pretty simple, actually. The algorithm is fairly straightforward. Here we see that the empirical breakpoint and the ground truth breakpoint is quite close to each other. They're only off by 0.2. So I think this is going to be a tighter match. I think this will be closer than, more accurate than the example I showed in the book figure. But, because these are random numbers, this sort of thing happens. Okay, so here I also extract the optimal breakpoint, and that's what I use here. So now notice that here all of this stuff is exactly the same as this code here. Or almost exactly the same. The difference is here I'm taking each breakpoint between x equals 2 and x equals 8. Here I'm only doing it once for the best breakpoint, the optimal breakpoint that we identified with our algorithm. Okay, and then I get y hat, which is our predicted data, and then some plotting. I won't go through the plotting line by line, but I hope it's pretty straightforward for you to read. Okay, so yeah, here you see the minimum occurred nicely at the center, and then we see that there's a pretty close correspondence between the true breakpoint in the solid line and the estimated breakpoint with the dashed line. So in this case, it worked quite well. The case in the book worked not quite as well, and there you actually saw a bit of a plateau. So there wasn't a really clear minimum peak. Or a trough. There wasn't really a trough here. It's kind of a plateau, and I think that's why we got this relatively largish gap here. Because I think what was happening is that, just because of some noise here, there's a bit of noise here, so that kind of screwed up the model estimation a little bit. And you can see that, this point here is technically the smallest, but it's not really clear whether any of these would be like statistically significantly larger. So there's some ambiguity, some uncertainty here. Here, the trough is a little bit closer to the center. Okay, the last thing I want to do here is just show you, this works really well. A lot of these optimization algorithms work really, really well when the noise isn't too intense. So I want to run this once more, but increasing the noise maybe to 0.5. Still not a huge amount of noise, but let's see what we get here. Okay, so here it's not quite as close, and let's see how the visualization looks. Okay, so here you see the two data points. The minimum, this is technically the smallest BIC, but it's a lot less compelling, right? We don't see this beautiful shape here. And here, this is not so far off, but it's also not so close. This is really where it should be. this solid line, and this is where the model estimated it to be. So if these were real data, then you might consider doing some pre-processing of these data. For example, trying to smooth the data. If you applied a smoothing filter to these data, then maybe you would get you would reduce some of the noise and get a slightly better estimate. Here we are in exercise 7 of chapter 15. This exercise is focused on the impact of outliers on regression analysis, in particular where the outlier is located, how that will impact the estimated slope from a simple regression, and the possible remediating effect of using robust regression or iteratively reweighted least squares regression. Okay, so to start with, simulate data using this wacky looking formula. So we have y, the observed data, equals e times x. E is the natural exponential, so it's 2.71 something. X is 40 linearly spaced numbers between 0 and 5. And of course, you know what pi is. And then epsilon is just random noise drawn from a standard normal distribution. Okay, so then you can compute a simple regression of x on y, plot the data and the predicted values. I'll show you this figure in a moment. Okay, so then in the experiment, you have a for loop that goes over all the data points. So we have 40 data points. So you're going to have a loop that goes over all of these 40 data points inside the loop. At each iteration of this loop, you add 10 to one data point. So in the first iteration, the first data point, so when x equals 0, becomes y, whatever this ends up being. I guess it just ends up being pi plus noise plus 10, right? So that's the outlier you're imposing only on data point 1. And then in the second iteration of the for loop, you add 10 to the second data point, so the second element in y, and so on, looping all the way through to the end. Okay, so then each time in each iteration, you're adding an outlier to a different element of the data, and then you want to fit the data again, store the beta coefficient. You don't need to worry about the model fit or the BIC or any of that. I mean, if you want to add all that stuff, that's great, but that's not what you need to do just for this exercise. Okay, but then you want to fit the data twice, once using OLS, which you are already familiar with, ordinary least squares, and then again using sm.rlm. So this is for reweighted linear models. This is a robust regression analysis that's provided in the stats models library. I discussed this a little bit in the book chapter towards the end of the chapter. I don't go into a lot of detail about the different algorithms and the mechanisms, but basically what this method is going to do is look through the data and identify any outliers and deweight them, so weigh them less so that they have less impact on the regression analysis and the beta terms. Okay, so then in a plot, you want to plot the ground truth slope, the estimated slope without any outlier, and all of the individual slopes for each iteration in this for loop. Okay, so let me show you that figure and make sure you understand what is going on here. So first we see in panel A is the data without any outliers added. So very simple, fairly uninteresting model actually, or data set. It's just we have a linear relationship between x and y, and then we have some noise. Now I'll show you B in a moment, but first I want to show you panels C and D. So this is illustrating two of the runs in this experiment. So at the first iteration, you take the very first data point and add 10 to it, and that's what you see here. And then at the second iteration in this for loop in this experiment, you take the second data point, add 10 to that one, and so on. So this is the what the data look like in the first iteration of the for loop. This is what the data look like at the final iteration of the for loop, where the outlier is all the way at the end. Okay, and then this is the best fit line. So you can already see that this outlier here is pulling up the slope here, right? These data points are not fit very well because this outlier, and these data points are also being underestimated by the model because of this outlier. Okay, so then we get to panel B. This shows the key results of this experiment. So what do we see here? This is the x-axis value where the outlier is located. Here on the y-axis, we see the beta coefficient. Now the dashed line, the dark gray dashed line here is the ground truth. That is this slope, that is E. This is the known ground truth without adding any noise in the dashed line. And then we see the beta coefficient without the outlier. So this is with noise, but with no outlier. And that is this slope here, the slope of this line. So this is our estimate of the relationship between x and y with the noise added, but without any outliers being introduced. Okay, you can see that that's a pretty good match. So, because the noise is randomly, normally distributed, both positive and negative, so should cancel out. You should see that the best fit line with noise is relatively close to the ground truth line. Okay, then we get to the interesting results. This is the beta coefficient, the slope of the relationship between x and y for each x-axis value where you introduce an outlier. So this data point here corresponds to this slope right here, the first data point. And then this data point over here corresponds to the slope here, where the outlier was in the final position. Okay, so it's interesting to see that with OLS, you get a lot of biases that are introduced by this outlier. So here, the outlier is early in the data set, and we find that it has a suppressive effect on the beta coefficient. It's shrinking the beta coefficient. Here, it's pulling the beta coefficient up. Now, that's not so surprising because of the way we are generating the outliers, but I think it's pretty remarkable to see this happening in action. And then what's super interesting is what happens with RLM, with the robust regression. You see that there is still a little bit of a bias, but the dampening effect, the algorithm of the robust regression is doing its job really well. So it's really getting rid of the impact of the outliers on these data. Now, this is interesting because the outlier is still included in the data set. We are not removing the outlier. We're not getting rid of the outlier, setting it to NaN and ignoring it, or just completely getting rid of that row. Instead, we are including that outlier. We are just shrinking the outlier so it has less of an impact on the final results. Okay, so that's pretty neat to see. Now I will switch to Python and show you my code solution. Here is where I simulate the data. It's actually pretty straightforward. This is the slope, and then I say y equals the slope times x, which is actually just the second column of the design matrix, plus pi plus random noise. Then I fit the model without adding any outlier, but with adding noise. And then here's where I run through the for loop that runs our experiment. So make a copy of the data because we do not want to destroy or keep adding the outlier over and over again in each iteration. We only want to change one data point at a time. So we're looping over all the data points, adding 10 to a copy of the data, and then fitting that copy of the data using OLS and RLM, and then plotting the results. So here I plot the original data and the predicted data, and here I'm plotting the beta coefficients for each of the two regression types. And then here's where I draw panels C and D. So basically this is looping over a for loop of two numbers where I specify just to add the outlier to the first data point or the final data point. Okay, so I think the coding isn't actually that interesting. You can look through it if you want, but the most important take-home message from this exercise is what I explained in when we were looking at the book Figure. So basically, the outliers do have a pretty strong impact on the slope of the regression fit, and the robust regression does a pretty good job at correcting for that bias. Now here you see the slope actually wasn't as good as it was in the example I showed in the book chapter. So basically, the noise here, just purely by chance, there happened to be a little bit more small values or negative values of noise here, so that pulled the beta coefficient down a little bit more. No, sorry, I was misreading that. So the beta coefficient is actually inflated. It's a little bit too high So there must have been some more noise up here. But anyway, you can see the key point is that the reweighted robust regression did a good job at attenuating the bias due to outliers. So now that you have this code, I encourage you to explore it more. Spend more time working with this code. You can see what happens when you add more noise, what happens if you add more outliers or negative outliers, what happens if these outliers are not always positive, but randomly positive and negative. Maybe, some of these will be randomly plus 10, some of these will be randomly minus 10, smaller outliers, larger outliers, and so on. I hope you enjoy working with this code and using it as a springboard to experiment with regression, impact of outliers, and remediation by robust regression. Welcome to exercise 8 of chapter 15. This exercise is quite long, it's quite involved, it has multiple parts. You can think of it more as like a project than an exercise. So I'm going to walk you through step by step. I'll be flipping back and forth between the text here and the code, and I'm going to try to explain this or guide you through this exercise as a bit of a narrative explanation. So the main point is to investigate the impact of heterogeneity of variance on the accuracy of the main regression outcome, which is the beta coefficient. So what we are going to do is simulate data repeatedly with different heterogeneity of variance characteristics and different amounts of variance. And we have to do this. We can only do an investigation like this using simulated data because we need to know the ground truth. Okay, so let's begin. To begin, you want to set up code that will simulate data according to this equation here. So y, the dependent variable, is m, which is a slope term, times x, which is the independent variable, plus v times phi. So all of these terms. So to start with, set m to be 1, v to be x, and phi to be standard normally distributed numbers. Now, initially, it seems a little weird to have m equals 1 and v equals x, but you will see later we are going to start manipulating these terms later in this exercise. Okay, so what does this mean? So we are multiplying x by noise, which means that the amount of noise is, or the variability is going to be a function of the independent variable x. And that is the way that we are manipulating or introducing heterogeneity of variance. So the variance is going to be small when x is close to 0, and the larger x gets, the larger the variance is going to be. So this is a violation of an assumption of a regression model, or really any kind of linear statistical model. Okay, so the first part of this exercise is to simulate data using these parameters and then make a plot and fit the data. Here you see the data and the predicted data. And here you can clearly see that the variability in y increases as a function of x. That violates a key assumption of regression models. Nonetheless, you see, it does look like there's some trend going on in here, which the regression analysis captures with this best fit line. Here are the predicted data. Here you see the residuals by the predicted data. As I mentioned before, by definition, this correlation is 0, but having a correlation coefficient of 0 doesn't mean that there is no relationship. It just means that there's no linear relationship. There's clearly this fanning out structure, which indicates heterogeneity of variance. Nonetheless, it's also actually interesting to see that the residuals are nicely Gaussian distributed. This is something that I've mentioned before. You should not rely only on one single metric to evaluate the outcome of a regression. It's good to look at multiple parts of the regression, look at the residuals in different ways, because it's possible that the residuals look really nice distribution, but they're still problematic. Okay, so there's more to this exercise, but I'm going to switch to code and just show you what I have up to this point so far. So here I'm generating the data. X goes from 0 to 7. And then here I set Y to be, actually I'm leaving the M term implicit here. But it's basically X plus noise, but the noise is modulated by X. So this is the term that I called V times phi in the equations in the book. Okay, and then add a constant. So this is creating the design matrix. It's a simple regression. Then we fit the model, extract the residuals and the predicted data values, and then do a little bit of plotting. So this is just recreating the figure that I already showed in the book. Okay, so now we can compare the ground truth data, which we know is 1, right? That's this value here, y equals x. So the slope is 1. Implicitly, there is a 1 times x, like this. Okay, so and then we're going to extract the actual slope that we get here. Okay, so the actual slope is 0.9. It's not super duper close. It's also not super duper far away. So I think, this is, well, I don't know how to evaluate how close this is. Actually, this one is even closer. So this is basically 1.1, a little bit less than 1.1. That's pretty close to the true value. So in this simulation, and also in the previous run that I ran, there is an indication that these data might not be appropriate for a regression because the assumption of homogeneity of variance is violated. But nonetheless, the estimated slope is still pretty accurate, pretty close to the true simulation slope. Now, for the next part of this exercise, we are going to systematically manipulate the amount of variance heterogeneity. So start by setting m equal to 2, and then we set v to be linearly spaced numbers from 1 to k, where k is going to vary between 1 and 10. So let me scroll back up to these equations to explain this in a little bit more detail. So we fix m at 2, that part's easy. And now here we have phi that's always staying the same, that's standard numbers. The question is, what is v equal to? So in the initial code that I just showed you, v was equal to x, which means that v is equal to linearly spaced numbers between 0 and 7. So what you want to do now is change v. So instead of v being equal to x, v is equal to linearly spaced numbers between 1 and k. And it's still going to go in 135 steps because that's how many data points we have. But v is no longer equal to x. V is equal to linearly spaced numbers between 1 and k, where k varies between 1 and 10. So that means at every iteration of this for loop, these terms are the same. This term is unique because it's random numbers, but it's always drawn from the same distribution. And what varies in each iteration of this for loop is basically the upper bound for v. So it's always going to be linearly spaced numbers starting at 1 and going up to numbers between 1 and, 1 and 10, I think. Yeah, 1 and 10. Okay, and then inside the for loop, you want to fit the regression model just like you have done already. And then we want to measure the error of the regression coefficient. And we measure that as the percent change from the empirical beta to the true slope that we know, which actually is just the number 2 here. Okay, so we compute this as percent change from 2, and then multiply, so this is the proportion, this gives us percent, and then we take the absolute value, and we take the absolute value because we are interested in the magnitude of the error. We don't really care about whether it's positive or negative. We just want to know whether it's still accurate or whether the accuracy of the beta coefficient relative to the true known slope is getting worse as we increase the variance heterogeneity. Okay, so you want to store this, and then you also want to store the statistical significance of the non-normality test. So you can take the p-value from the omnibus test and calculate it or store it as minus log p. So the logarithm of the p-values, as you know, will stretch out the p-values. It helps us interpret very, very small p-values. And then taking the minus sign is something that people do sometimes. It just flips the sign. So now larger values correspond to smaller p-values. Here I have a little footnote. This is just a little note about sm.ols. So it turns out that all of the model diagnostics are not computed automatically. They're only computed when you run model.summary. So if you do not run model.summary or MDL, this I'm calling this variable MDL. This is the output of statsmodels.ols. The raw output of statsmodels.ols does not have a diagnostic dictionary. You first need to run model.summary, and then this dictionary is calculated and populated. The last thing to do in this experiment is basically just to rerun each of these iterations 20 times. And the goal of, or the purpose of rerunning it 20 times is just to get a little bit more stability. The beta errors can be positive and negative. Because it's random noise, sometimes the heterogeneity of variance will be a little bit worse, sometimes it'll be a little bit better. So just repeat every iteration in this experiment 20 times and average all of the results together. And that's what you see in this plot here. So panel A shows the error in the coefficient estimate. So we have the this is the parameter k here, like the badness of the heterogeneity. This is no heterogeneity. This is lots of heterogeneity of variance. And this is the percent error in the regression coefficient relative to the ground truth, which we know is m equals 2. Okay, so you see as the homogeneity or heterogeneity increases, as the heteroscedasticity increases, the error is more and more extreme. So we get up to over 10% error in the estimate of the beta coefficient due to this fanning of the variance as a function of the x variable. And here, this is the statistical significance of non-normality of the residuals. So here you see, that the more heteroscedastic the data are, the more significant the non-normality of the residuals become. So this is indicating that something bad is going on. Of course, this is a metric that you don't have access to in real data because you don't know the ground truth in real data. Okay, so there's still more to do in this exercise, but first I want to switch to Python and show you this code here. So we have the slope, we have the number of repetitions, this is the badness, this is what I called parameter k when I was describing this. Okay, so then let's see, ignore this for the moment. I'm going to get back to this in a little bit. So here I have the for loop over the different values of k, which is the extremeness of the heterogeneity of variance. And here I'm looping over the 20 different repetitions. Okay, so ignore this for now. I will get back to this in a moment. Right now, we are just focusing on the first simulation. So here you can see I'm defining a noise term. It is random numbers. So this is our just random standard normal distribution of noise times linearly spaced numbers from 1 to max bad. This is the each element in badness. Again, that's the parameter that I called k. Okay, and then we have y equals mx plus the noise. Fit the model, test the summary, so we get the diagnostic information. Here is the error of the beta term and the minus log of the p of the omnibus. Test for the residuals, exactly as I explained in the book. Okay, so you can see here I'm summing all of these terms, and here I'm dividing by the number of repetitions to give the average. Okay, and then some plotting. Now, what do we see here? What we see is that the heterogeneity of variance is having a really significant negative impact on the accuracy of the beta coefficients. So the coefficient estimate is getting worse the more heteroscedasticity we have in our data. Now, before you get too concerned about this or make too big of a deal out of this, let me switch back to the book and explain the next part of the exercise. So it turns out that there is a problem with the interpretation. There is a confound in the experiment. If you would like to pause the video, see if you can come up with it without reading the next paragraph, then feel free to do that. Okay, so here is the problem. We are not only manipulating the heteroscedasticity of the data, we are also manipulating the total amount of variance. And that is because, let me go back up to these model equations here. That is because as the k parameter, the maximum value in this linearly spaced scaling, increases, that also increases the total variance. So we're not only increasing the distribution of variance, we're also increasing the total amount of variance. So that is a confound in this experiment. And so this brings us to the last part of this exercise, which is to modify the code in the for loop twice. You want to modify it once to have to manipulate the total variance without changing the heteroscedasticity of the variance. So basically have homogeneity of variance, but manipulating the total variance across the entire data set. That's one. And then the second is to keep the total amount of variance the same, but change the amount of the homogeneity of variance. So basically, the initial simulation that we did had two factors manipulated at the same time, total variance and homogeneity of variance. And now I want you to run two more simulations. First, where you isolate the amount of variance without manipulating the homogeneity of variance, and a second one where you manipulate the homogeneity of variance without changing the total amount of variance. Okay, so now I'll switch back to Python, show you that code, and then have a discussion. So here is where we get to this variable here called noise simulation. So when noise simulation equals 1, that was what I already showed you, where we manipulate both the total variance and the heterogeneity of variance. Here in noise simulation 2, you can see I have this linearly spaced numbers from max bad to max bad. So that means we're just changing the overall amount of noise, the overall variance of the noise without changing the homogeneity of the noise, because this is going to be a constant. In fact, you can really just multiply this by max bad. I think I just set it to go max bad to max bad just in the interest of, having the code look parallel. Okay, so now let's run. Actually, let me just remind you very quickly. So basically what we saw here with this confounded experiment is that the error increases with heteroscedasticity. Okay, so now I'm just going to change 1 to 2, and then we see basically the same effect. So again, the percent error in the beta coefficients is increasing. Now this label is no longer correct. This is just the total amount of variance. It's not the maximum heteroscedasticity. But what's interesting here is that you see that the residual non-normality p-values are all very small here, which means, so the minus log of the p-values is large, which means the p-values are very, the minus log of the p-values is small, so the p-values are very large, this would be the statistical significance threshold. This indicates that none of these tests showed significant inhomogeneity of variance. So the variance, the variance of the residuals looks great, but we still get this problem with the error in the beta coefficient accuracy. Okay, so now let's do noise simulation 3. And what's happening in noise simulation 3 is that I generate the noise here exactly the same way as I do here, right? So this line of code and this line of code is the same. So at this point, we still have this coupling, this confound between the heterogeneity of variance and the total amount of variance. And then what I do is scale down the total amount of variance in this noise term so that it has unit standard deviation. So that means that this is going to be, the variance is going to change across the x-axis, but the total amount of variance that we add to the data is always going to have a standard deviation of 1. So we are fixing the total amount of noise while manipulating the homogeneity of noise. And here what you see is, if you look at panel B first, you can see that the manipulation worked in the sense that the p-values were significant for this residual omnibus test. So this is a statistically significant heterogeneity of variance, which is bad. But you see that there is no systematic variant error in the beta coefficient as a function of the heteroscedasticity. So the error is fairly small. It's around 2%, easily attributable just to adding any noise to any data. So yeah, I think this is pretty interesting. What this tells you is that heterogeneity of variance is a violation of the assumption of a regression, but it's not necessarily so detrimental to the accuracy of the beta coefficients. Again, one of the themes here is that you should try to get your data to conform to assumptions of inferential statistics and parametric statistics, but if the data do violate the assumptions, that's not necessarily a terrible thing. You can still get pretty decent results from your statistical models, even if your data violate the assumptions of those models. Here in exercise 9 of chapter 15, we are going to focus on using regression to perform interpolation or extrapolation. More generally, this is called predictive modeling. The idea is that you create a statistical model, a regression model, you fit that model to some data, and then you apply the model to other data points that you have not observed. So basically, you're faking data. You're making up data based on a model that has parameters that were fit to data that you actually did observe. Okay, now actually, we're going to be using all fake data here. So we're using some fake data to generate predictions about other fake data that we could have measured but didn't actually measure. Okay, so here is the setup. I have a whole story behind this exercise just to make things a little bit more fun. So imagine you are a freelance data scientist. You're hired by an ice cream shop to analyze data from an experiment that they conducted. So this is actually pretty typical for being a professional data scientist, that you're not really collecting the data yourself. Other people have conducted experiments or gathered observations from online, from research projects, and they hire you to analyze their data. Okay, so this ice cream shop wants a predictive model of sales based on the temperature. So this makes sense, right? When it's cold out, not people do eat ice cream when it's cold out, but not as much as when it's warm out. And the price of an ice cream cone. And here I'm basing my thinking on also the price being a nonlinear function. So when ice cream is really, really cheap, then people are suspicious because why is this ice cream so cheap? But if it's really expensive, then obviously you're going to get fewer people buying it because they're priced out. Okay, so over the course of a year, this ice cream shop manipulates their prices. So they change the price, they measure the outside temperature, they generate a big data set, and they give it to you. Okay, so, and then basically you have to analyze those data. So there's actually a couple of parts. There's 3 parts to this exercise. The first part is to simulate the data. The second part is to analyze the data with a regression and confirm that the beta coefficients you get match the simulated parameters. And the third part of this exercise is to perform interpolation or predictive modeling. So here is the formula that you are going to use. This is the Ford model that you will use to generate the data. This is the first part of this exercise. So Y is sales equals 50. This is the intercept plus beta T times T, where T is the temperature, and then beta P times P minus 4 squared. And this is price. So this is the coefficient for price, and this is the price term. And then we have some noise here. Now notice that there is a nonlinearity in this model. However, the nonlinearity is not on the beta coefficient. The nonlinearity is on the independent variable. So it's totally fine. The beta coefficient is still linear. So it's just, multiplied here. So that means we can still perform a linear regression on this data set. So what you need to do now is create some data using this formula where beta t is 2, beta p is -3, and epsilon is noise with a mean of 0, or drawn from a population with a mean of 0 and a variance of 4. Okay, so now you want to have enough data points so that the temperature, which is this variable t, uh, ranges from 10 to 35, and the price ranges from 1 to 8 in integer steps. So you want to make sure that you have enough data points to have all combinations of temperature and price. So it doesn't make sense if you only have temperature equals 10 and one observation where temperature is 10 degrees and the price of the ice cream is €1. So you're also going to need some data where the temperature is 10 degrees and the price is €2, 10 degrees and €3, 10 degrees and €4, and so on. All the possible combinations of temperature and price need to be included in your simulated data set with a sample size of 250. Okay, so then what you want to do is generate a figure that looks like this. So these are the data. These are the simulated data. You have temperature on the x-axis, the price per cone on the color axis. So more expensive ice cream is red and less expensive ice cream is blue. And then you can see it goes to white in the middle. And then we have the ice cream sales on the y-axis. This is the dependent variable. And what you see in this plot is, of course, a very clear main effect of temperature. So as temperature increases, ice cream sales also increase. That's a linear effect. But then you also see this quadratic effect of the price per ice cream cone. And that quadratic effect is reflected in the fact that the dark red and dark blue colors are lower and the pale colors are higher, right? So you have this gradient here, this like vertical gradient where the color intensity is greater when the ice cream, when the color is more extreme. So basically that means that very cheap ice cream and very expensive ice cream doesn't sell as well. And ice cream sales closer to 4.5, those get higher sales. Okay, so again, your first task is to simulate these data to produce this plot. And I'm now going to switch to Python. I will show you two things. I'll show you my code to generate the data in this plot, and then I will show you running that data through a regression where we try to see what coefficients we actually observe given the simulated ground truth data. So here I have a variable called temp, which is tiles. So this is basically repeating over and over again. So it's the numbers 10 through 35 in 25 steps. This is the temperature. And then this vector here, this linearly spaced vector from 10 to 35 repeats 10 times. So that's going to be 250 repetitions of going 10 to 35, 10 to 35, 10 to 35. And then within that, I have this vector of price, which goes from 0.1 to 8 in 250 steps, but then I'm rounding up. So this is actually going to be integers from 1 through 8 in 250 steps in integers. And then when we combine temp and price, we're going to get all of the combinations of temperature and price. Here I'm specifying the beta values, and here is some noise. Okay, so here is the dependent variable, which I create using this forward model. So again, nothing super tricky here. This is just a direct implementation of the formula that I showed in the book. Just make sure that you are really squaring price shifted by 4. Okay, so then I'm using a scatter plot to generate the dots where I have temperature on the x-axis, sales on the y-axis, and the color is defined by the price. So there we go. Okay, so here are the data. And now here's the design matrix for the regression model. You see I have sales, I have an intercept, temperature, price. Again, make sure you are listing the price using this quadratic function, this expression, price minus 4, and then that quantity squared. And then I have the interaction term, temperature versus price. Now, this is pretty interesting because I did not include this interaction term in the model, right? The forward model, the way I generated the data, do not include an interaction term. There are two independent effects of temperature and price. Nonetheless, I am including an interaction term in the statistical model. So be interesting to see what that looks like. yeah, here you just see the data frame here. So you can match your result against this, make sure you're getting the correct data frame. Okay, then here I fit the model, pretty straightforward, and then look at the model output. And what we see is that the model is highly statistically significant. We get an intercept around 0. Temperature beta is 2. The price beta is minus 2.95, very, very close to 3. And the interaction term is basically 0. And the p-value is greater than 0.05. So this is as expected. We should not see a statistically significant p-value here for the interaction term. So that completes the first two parts of this exercise. Now we have the third part, which is interpolation or predictive modeling. So now the idea is that once we have this statistical model, once we have fit the parameters to the data, and we have checked against the ground truth that the parameters are accurate, so the model was a good fit to the data, now we can use model.predict. So model would be the output of sm.ols. And we can input any set of variables that we want, any set of predictors, and get the predicted outcome. Now, this is literally exactly the same method that we have been using to generate the predicted data. So previously, we have been inputting the design matrix in here. So there's nothing new here, conceptually, mathematically. The only little difference is just about the implementation, where instead of inputting the design matrix, as we've always done to get predicted data, we are going to input new numbers that were not actually measured. So 25 degrees Celsius and 6.5 euros. So what is the expected sales volume for 25 degrees and 6.5 euros, given that we didn't actually measure 6.5 euros? Okay, so then you can plot the prediction here. It looks pretty reasonable. They have a predicted data point that's snugly inside the distribution here. So this is certainly not very surprising. But of course, the main point is to have the code and understand the concept of interpolation and predictive modeling. So that's what we have here. Now I'm using model.predict. And now in this case, again, as I mentioned, normally so far in this chapter, we have been inputting the design matrix. Here, we've been doing this, inputting the design matrix. Here, we input a vector. And what is this vector? It is 1, the predicted temperature, the predicted price, and 0. And what do these numbers correspond to? These are the columns in the design matrix. So this is the intercept, this is the temperature, this is the price, and this is the interaction. Again, we're not modeling an interaction, so we just set that to be 0. So this is our predicted data value for some measurement that we have not actually recorded. Okay, and then the rest of this code is not that interesting. It's just reproducing this figure exactly how I showed it in the book. Welcome to exercise 10 of chapter 15. This exercise and the next exercise go hand in hand. We're going to work with some real data. It's the same data set in both exercises. The goal of this exercise is to import the data, visualize the data, process the data, apply some transformations, clean the data, visually inspect the data, all sorts of things, just about the data, no inferential statistics. And then the next exercise, exercise 11, is going to be all about fitting a regression model or building a regression model, fitting that model to the data, and interpreting the results. Okay, so this data set is another data set I found online. It's freely available. It's about the sales of apartments in Tehran, in Iran. And it's quite a big data set. There's lots and lots of features. So lots of ways you could combine the data. You can select data, many variables to use for an independent variable, many possibilities for a dependent variable. So what I chose to use here is the sale price, the apartment size, which is measured as floor area, the interest rate of the banks at the time of the sale, and the CPI, which is Consumer Price Index. If you're not familiar with Consumer Price Index, it's a measure used in econometrics, basically to determine how much things cost. The way they calculate it is just they go around and figure out how much does a bar of soap cost? How much do cherries cost? How much does a washing machine cost? all sorts of little things and big things, and they put it all together and say, what is the general price of existing in modern human society? So you want to import the data, extract these four features, and then, so actually part of this is just figuring out how to import the data. In the first place, the data actually come in a zip file with that contains an Excel file format. So there's a little bit of work that you need to do. I didn't keep track of how long exactly it took me to finagle this data set into Pandas, but it was many minutes. So importing these data is not going to be as straightforward as in other cases, but that is part of doing data science in practice in the real world. Okay, and yeah, if you're struggling with this, this is Python code. It's Pandas code. It has nothing to do with statistics. It's all about working with data in using Pandas. So if you're struggling with this part of the exercise, feel free to just look at my code and copy it. So then you can focus more on the statistics concepts. Okay, so then the final data set when you import it should look like this. We have 4 columns. These are the row indices, 4 columns for floor area, interest rate, CPI, and the price of the apartment. Now, once you have imported the data, you want to use the pair plot function in Seaborn. It's a bit of a mouthful there. The pair plot function in Seaborn, and that is going to produce a figure that looks like this. Now, once you get to this figure, this is where your exploration of the data could deviate from mine. So basically what you want to do here is look at the data, make some decisions about whether and how to transform the data, whether and how to clean the data. And I want you to have the freedom to do it. I am going to explain the steps that I took based on my decisions, based on inspecting these data. But it's perfectly fine if you look at the data and you come to different decisions, you apply different transformations. That's completely fine. You're almost done the book, so you've done amazing. You've learned a ton about statistics, and you can make your own decisions. All right, all that said, I'm now going to switch to Python, show you my code, and explain the transformations that I applied to the data. Okay, here is the website reference for the data set where you can read about the data. You can download the data manually. I actually did have to download the zip file manually, open it up, look at the Excel file, and look through all the columns to figure out which columns I actually wanted. So it turns out that columns F, V, AA, and D are the columns that correspond to these variables. That is not something that you would know just from running this code. You have to literally open up the Excel file and look through the Excel file and consult back on the website and so on to figure this stuff out. Okay, so then the final solution, the way that I import these data after having already done some manual inspection, is to download the zip file onto the server here where this Colab is running, and then unpack it. So now I'm unpacking that zip file, and then I can import it locally. So run this code here, and then we get this data file here. So again, it looks very simple, but there is quite a bit of manual effort that went in between, this line of code and all of these lines of code. All right, so now we have the data, and now I'm going to visualize the data with pair plot. Okay, so a couple of things we can infer from this plot. Maybe I'll zoom out a little bit. A couple of things we can infer. One, when I look at these distributions, there's clearly a very long tail. To me, this looks like a typical situation where applying a log transform is going to make these data more normally distributed. Same thing with price here. So I'm going to log transform these data variables. And also you can see that interest rate is only existing in integer values, and there's only 1, 2, 3, 4 possible values for interest rate. And furthermore, interest rate, here's the best way to look at it. Interest rate is clearly non-Gaussian distributed. So based on the distribution, based on the limited number of unique values, I decided to median split these data, or to cut the data right here, and binarize interest. So I get these and these. Actually, sorry, I just checked. So I cut it here. So I have 15 interest rate of 15% and an interest rate less than 15%. So all of these get grouped together. We can call this relatively low interest rate. and this is relatively high interest rate. Okay, so these were the decisions that I made. Here you can see I'm computing log price, log floor area, and binarizing the interest. This plus 0 here is to convert from Boolean. So this is a Boolean, and then we add 0. It's just a little trick in Python to convert false and true to 0 and 1. Okay, and then we can look at this again and notice that I didn't overwrite these variables. I created new columns in the data frame so that we don't overwrite the original data. And that's good because it allows us to continue exploring, these transformations. So now for another plot. So this is exactly the same pair plot, except I'm using the log data instead of the original data. This looks much, much better. Here you see really nice Gaussian distributions. Here and here, CPI I left as its own distribution. Not perfectly Gaussian, but I think this still looks pretty reasonable. Okay, we can also see some robust relationships between the variables like price and CPI. This is not so surprising. Log price is the price of an apartment. An apartment is a thing that people buy, and CPI is a measure of things that people buy. Now, I don't know enough about the Iranian economy and metrics of the Iranian economy to say that this is redundant. And that's because CPI, there's many different ways of measuring CPI. Different economists, different institutions, different governments will measure CPI in slightly different ways. So I don't know if in Iran they compute CPI including housing prices or excluding housing prices. Either way, it's still not that surprising here. Okay, now when I looked at these data, it looks like there's some outliers floating around in here. So therefore, I decided to, let me get back to the original. I decided to Z-score the data and then create a new, actually, let me just show you the box plots of all the data. So these are the continuous variables here, log price, log floor area, and CPI. They're Z-scored, so they're centered at 0, the mean of 1, and this is the threshold that I used for removing outliers. So you can see there are 3 outliers here, and I chose to remove those outliers row-wise. So the entire row is gone. And this is just reporting that change in the number of rows. So the original data has however many rows it has, and then the post-cleaned data has a different number of rows because I have removed these. Okay, I guess it was 4. Is there 4? Okay, well, it looks like only 3 to me, but maybe there's another data point floating in here. Anyway, so these were the 2 transformations that I applied to the data. The log transform, I guess 3 transformations. The log transform, binarizing interest rate, and cleaning according to Z-score. So now we can inspect the correlation matrix. And let's see, the diagonals are 1s, of course. We see a pretty broad range of correlations across the different variables. Now you have to keep in mind here that some of these correlations are a little bit trivial. For example, the correlation between log floor area and floor area is 0.9. No surprise. It's literally the same data, just log transformed. Of course, this is not 1. The correlation is not 1 because we applied a nonlinear transform and correlation is a linear measure. So they're still strongly related to each other. Of course, the Spearman correlation would be 1. But other correlations are interesting to observe. For example, between log price and log floor area. So this is going to be the dependent variable. This is one of the independent variables. That has a correlation of 0.3. I'm not performing any inferential statistics. There's no p-values here. But 0.3, I think with a sample size of almost 400, this is almost certainly going to be statistically significant. So this concludes exercise 11. Again, it is possible that you made different decisions about how to transform and process the data than what I did. And that's great. That means that you're already thinking for yourself. You're working your way towards being an independent statistician or a data science practitioner. And now we are ready for the next exercise where we will analyze these data. Here we are with exercise 11 in chapter 15. This is a follow-up to the previous exercise. You definitely need to have done exercise 10 in order to complete exercise 11. And also the next exercise is using the same data set. And I forgot to mention that in the beginning of the previous exercise. Anyway, so the goal of exercise 10 was to import and process the data. And now in exercise 11, you are going to perform a regression. So you want to construct a design matrix that includes the intercept, the floor area, interest rate, and CPI, and the interaction between CPI and interest rate. Now, if you applied any transformations to the data like I did, then make sure you are using the transformed data and not the raw data. So, but if you kept the data in their raw format, then that's fine. Then use the raw thing. Okay, so again, the intercept, floor area, interest rate, CPI, and the interaction between CPI and interest. So those are your independent variables. The dependent variable is the sale price of the apartment. Okay, so then you can run the regression and make some interpretations and I see what happens. Maybe, if you applied the same transformations I applied, you will also get a warning message about the condition number of the design matrix. Now, maybe you get this or maybe you don't, depending on what transformations you applied. Okay, so let's see, I'm going to have a few remarks to say about this, and this will also be relevant for the next exercise. So then what you want to do is visualize the data and the output of the model. Again, I would encourage you to visualize the data and the model residuals and predictions however you like. You don't have to do exactly the visualizations that I'm using. Here's how my plot looks. And I'm going to explain and interpret these results in a moment when I generate this plot in Python. So here I add a new column to the data frame. I call that intercept. It's just all ones. Here is an interaction term. So this is the interaction between interest rate and CPI. That is literally just the product of those two variables. The only thing you have to be mindful of is to use the columns that are transformed and not the original data columns. Okay, and then here I'm creating the design matrix, and that is basically the data frame, but then I'm dropping all of the irrelevant columns. So we don't need log price, that's a dependent variable. We don't need price, we don't need the original floor area or interest rate because we are using the log transformed versions of floor area and the binarized interest rate. Okay, and then of course log price is the dependent variable design matrix. And here we have our regression summary table. So we have a adjusted R² of 0.6. In this case, the regular R² is also more or less the same. A really, really big F value and a tiny, look at this p-value, 10 to the minus 75. That's a ridiculously small number. Okay, so this indicates that the model was a good fit to the data. And then you see that actually all of the predictors were statistically significant. Now, without really understanding the units of the data, it's hard to interpret the actual coefficients themselves, but we can interpret the sign. So you can always interpret the sign and the statistical significance of a coefficient, even if you don't know exactly how to interpret the numerical value. And that's especially the case in this data set because we applied a logarithmic transformation. So we applied a nonlinear transformation. And of course, these coefficients are linear. So the numbers themselves might be difficult to interpret, but certainly the sign we can interpret. So this one is pretty interesting. Actually, the rest of these are pretty straightforward to interpret. So as the CPI increases, the price of houses increase. That makes sense. When things are more expensive, houses are also more expensive. The positive coefficient with floor area also makes sense. The more area an apartment has, the bigger the sale price. And this one is also sensible that it's negative. So the higher the interest rate, the less the sale price. So that's because you're already paying a lot of interest to the bank. So you don't want to pay as much for the apartment. Okay, so then here we see the diagnostics. This one is non-significant, which is good. That suggests that the residuals are normally distributed. This one is technically statistically significant. So that's not good. Be nice if that were also non-significant. but it's not, I don't think this is such a big deal. And in fact, I'm going to plot the residuals in a moment. Okay, here we see this warning about the condition number being large. As I discussed in the book, a large condition number for the design matrix is not necessarily problematic. It can mean one of two things. One, it can mean that there are problems with the independent variables, and the model is difficult to fit. And adding or dropping one additional observation can have an outsized impact on the model parameters. So that's one possibility. But another possibility is that the condition number is large for no other reason than the different variables have different scales. And we know that that is the case here. CPI and interest rate, floor area, these all have very different numerical scales, although less so after log transform. But still, the numerical scales are quite different. This is a concept that we are going to explore in the next exercise. So I'm just going to leave it there for now. Okay, so then here I generate the plot. I don't want to spend a lot of time talking about exactly, all these plotting codes, but I encourage you to look through all of the code, make sure you understand how I'm generating or how these lines of code are corresponding to the different elements of the plot. So I will just speak of these more conceptually and say that, so here I'm plotting price by CPI, separated according to the interest rate, whether the interest rate was less than 15% or greater than 15%. Now, you probably expected to see a line going through here instead of this curvy looking, funny looking line here. But this is because we have a multi-dimensional model. We have a high dimensional model, and I'm only showing 2 dimensions on this plot separated by a third binary dimension. So there's actually a lot more going on in the full multidimensional space that we are not visualizing here. So this is just a projection down, ignoring the floor price. That's what's causing these fluctuations here is the changes in the floor price, which I'm not visualizing in the plot. Over here in panel B, you see the observed dependent variable by the predicted dependent variable. And overall, this looks pretty good. There's maybe some weird things going on here, some outliers or a floor effect, but most of the data appear to be lying on a line here, which is good. So the predicted data match the observed data pretty closely. Here I have the residuals plot. So again, this is the predicted data, the predicted price of the apartment by the residuals. And as I mentioned many times before, what you're looking for here is structure in these in the residuals. If you see structure, then that's something concerning. If you don't see any structure, then that's a good sign. To me, this looks like a big homogeneous cloud of information. So it does seem to be a little bit of a bias or tendency for low interest rates to be higher and high interest rates to be lower. That's not surprising, but overall, this looks quite good. And here you see the histogram of the two of the residuals for the two binarized interest rates, and these look great. I mean, you saw that the omnibus test for normality was 0.042. So that suggests that the data were technically, statistically significantly non-normally distributed. But as I've mentioned in previous chapters, this omnibus test or any test of normality can sometimes give a statistically significant result, so a small p-value, even if the data are quite close to a normal distribution if the sample size is high. Okay, so I hope you enjoyed working through this exercise. Again, your results might look different from mine if you made different choices in this and the previous video about how to process and analyze the data. In the next exercise, we are going to explore the magnitudes of the beta coefficients and in particular, multiple ways of standardizing the beta coefficients. Welcome to exercise 12 of chapter 15. Here is the final follow-up, the third of 3 exercises using the same data set. Obviously, you need to have conducted the previous 2 exercises in order to do this one. Okay, so we see that the regressor's beta values vary by several orders of magnitude, and that's because the predictor variables have very different numerical scales. I'll show you that in a moment. And then So therefore, the goal of this exercise is to standardize the beta coefficients so they can be directly numerically compared. Now, you learned in this chapter that there are two ways to standardize beta coefficients. You can either standardize all the variables and then run a regression, or you can use the standard deviations from the variables to scale the unstandardized betas. And that I showed in equation 28. So I'll scroll up and show equation 28. So what you want to do is implement both of these methods. So standardize the data and rerun the regression, and then run the unstandardized regression and standardize the beta coefficients using the standard deviations of the variables. So let me first scroll up to show you what I am referring to about the coefficients. So you can see that there's basically like 3 orders of magnitude variability across the different coefficients. So lots of variability, numerical differences between the smallest coefficients and the largest coefficients. Here is equation 28, where you see that to get from the unstandardized beta coefficient to the standardized beta coefficient, you need to multiply by the ratio of the standard deviations, the sample standard deviations of this particular variable in the design matrix and the dependent variable. So the two variables that are involved, the independent variable and the dependent variable. And this is how you get from unstandardized to standardized coefficient. So the code here is relatively straightforward. Basically, we just want to change all of the variables that we need here. So CPI, log floor area, log price, interest rate, and the interaction term. And so these are the names of the columns that I want to z-score. And then here I'm saying that there's a new data frame, which is a copy of the data. And then I'm literally just overwriting these variables with their z-scored version. So the data minus the mean divided by the standard deviation. So this is the way that I chose to do it in a separate data frame. If you want, you could also use the same data frame, but have other columns. So you could call this, something like this, create new columns for z-scored or standardized versions. That's also completely fine. There's no particular right or wrong way to do it. Okay, so then I'm running the regression. This is the same exact regression, but now I'm calling it model STD for standardized. So this gives me the standardized beta coefficients. I will talk about these in a moment. Here I have the original model. So that was the model that we ran in the previous exercise. These are the unstandardized coefficients. These are the standardized coefficients. And then I am taking the unstandardized coefficients, multiplying by the standard deviation of the corresponding column, dividing by the standard deviation of the dependent variable. Okay, so this is the other way of computing the standardized beta coefficient, and then I'm printing everything out in this nice little table here. So what do we see in this table? Let me scroll down. Where does this table go? Okay, so here is the variable in the first column, the unstandardized coefficients, the standardized coefficients by standardizing the coefficients, and standardization by standardizing the data. Okay, so these match. These are exactly the same numbers, and that shows that to get these standardized coefficients, you can standardize the data, or you can standardize the unstandardized coefficients. Either way is exactly the same. There's no difference. There's just no, it's whatever you prefer. If you want to have access to the unstandardized coefficients, obviously, then this is the way to go. Now, you should not be surprised that the intercept term goes to 0. Everything is standardized. Every variable has a mean of 0. So therefore, the intercept term is by definition 0. It cannot be any other way. I guess it can be differently if you didn't do the standardization correctly. Okay, so now the last thing I want to do in this exercise in this code is go back to the condition number. Remember that we got a warning up here in the previous exercise. We got a warning that the condition number is large. This might indicate that there is multicollinearity or other numerical problems. But interestingly, here We did not see the same warning. So there's no warning about the condition number, despite the fact that it is exactly the same data, exactly the same model, exactly the same coefficients. The only thing we've done differently is standardize all the variables. So now all of the independent variables are in the same numerical scale. And now we don't get that warning anymore. So let's see what are the condition numbers of the design matrices. Here for the unstandardized design matrix, it's over 1,000. For the standardized design matrix, it's 5. So the coefficients, when we standardize them, are exactly the same. You can go back and compare these, the model fit to the data. That's exactly the same. In fact, you remember I discussed this in the previous video, and I said that the F statistic is so huge, the p-value is tiny. So all this stuff is the same. But the condition number of the design matrix is much, much smaller, orders of magnitude smaller. So this tells us that the warning message we got in the previous exercise was actually not a problem. It was not a problem with the multicollinearity. There was no problem with the design matrix. It was just that the condition number was large because the independent variables had different numerical ranges. And that tells us that we actually do not need to worry about this. It's not the big concern. It doesn't indicate anything wrong with the model.